creepy screen and back. Hello again. Now recording at home. All right, so let's see how we did here. There. Number 1, model predicted outcome when time equals 4. So here's the model we're looking at, fixed intercept of 10, instantaneous linear slope when time equals 0 of 3, and a quadratic of -0.5, fixed quadratic. So to figure out what the model says the outcome should be at time equals 4, you plug in 4 everywhere where it says time. So this is no different than what you learned how to do in any other linear models class to create predicted outcomes. So it would work out to be 14. Okay, with me so far? All right, cool. Yes, now, how to ask SAS to do that for you. I asked you to figure it out yourself so that you could then hopefully translate this logic into a programming statement. So every time you see a word here in an estimate statement, it's referring to the fixed effect that goes with that word. So it's plugging in the coefficients 10, 3, and -0.5 respectively for each of these words. So to create a predicted outcome, it just needs to know how to combine the fixed effects. So in my equation here, I had 10, so that's my intercept 1. I need 1, 10 to start with. I need 4 linear slopes, and I need 16 quadratic slopes. When you put that all together, it would spit out this 14 along with the standard error and its p-value for whether or not it's different than 0. Okay. Any questions on that? All right. Now the trickier ones. What is the model predicted linear rate of change when time equals 4? So we forget the fixed intercept because that has nothing to do with what the linear effect of time will be at any occasion, and we focus only on this part. So the linear effect of time at time 0 itself would be 3. From there, we have to figure out what it would be at time 4 instead. So it is the quadratic fixed effect times the value of time at the desired occasion. And then we throw in a 2 because twice the quadratic is how the linear slope changes per unit time. That works out to be -1. That same idea implemented as an estimate statement means I need 1 of the linear fixed slopes, so I need 1 value of 3, and then I need 8 of the quadratic slopes because I have a time equals 4 times 2. And it knows that time by time is a negative value in this model, so it holds the negative value already. Okay, questions on that one? All right. Last one. Sort of a trick question, but not really. What is the model predicted quadratic rate of change at time equals 4? If you look at this equation, how many times does time by time show up? How many instances of time by time do you see in this model? Just 1, right? That means it is unconditional. It doesn't interact with anything, so -0.5 is the effective quadratic time all the time. So what is the model predicted quadratic rate of change, period? It's that. At time 1, at time 4, at time 3, at time 2, at time whatever. So you wouldn't actually need an estimate statement because it shows up by default on the output. But if you were to write one, you would just list that fixed effect, and you need 1 of those. Cool. Sometimes when I'm doing something that I know is complicated and that I'm likely to forget what it is later on, I will write estimate statements that look like this. That way later on, I don't have to refigure out what the coefficient means if it's a complicated model. I will leave myself a trail of breadcrumbs with an estimate statement with a label so that it provides a ready interpretation for whatever I'm doing, even if it's already provided by the model. That way you don't have to combine across 2 different tables of output to get everything that you might want to know. Questions? Please.
So is it not exponential?
Not what? I'm sorry?
Is it decelerating?
Accelerating?
It's not accelerating.
In this instance, I would call it decelerating because it's making the linear slope that was positive less positive as time goes on. Other questions? So how did that go? Was that hard? No one wants to admit it was hard. It's okay. This is a good example of the kind of thing that we're going to have to start doing when we get predictors into our model, which is coming up actually next time, just reviewing it in the concept of regular linear models and then putting it into longitudinal models. Because longitudinal models get complicated very quickly. And anytime you ask a research question involving differences in change, do different kinds of people change differently? At a minimum, that's a two-way interaction. Maddie, I love your face. She's like, no. Like, it's tricky at first. It's one of those things that has a learning curve. But the good news is that eventually you will see it and then you can't unsee it. It will take us some practice to get there. So that's why I wanted to start with a reminder of how we do this, and this will show up as the weeks progress whenever we talk about predicted values and predicted linear slopes for particular kinds of people or at particular occasions. So, homework 5 I looked at, that seemed to go pretty well. I have an example up here if anybody wants to ask any questions about it. Do you want to go over it? Yes or no? Yes, Amy says yes. All right, Amy, this one's for you. Thank you for being emphatic. All right, so let's see. Saturated mean unstructured variance model was the first thing I asked. Are there significant mean differences across month? That's an F-test that shows up by default on your output if you use SAS. If you enter the time variable on the class statement, it's treated as a categorical predictor. The model computes a multivariate wall test for all the differences across time. Number of occasions -1 for the degrees of freedom. If you ask for LS means, you can get the mean amount at any particular occasion, and total amount of variation would either be in the R matrix or the V matrix, depending on how you set up your model. Let's see, empty means random intercept. This one, I answered so many questions on this one. That right here, the effect size for the amount of person dependency and well-being. Yeah, there's actually 2 different slides you could find that say this explicitly, but I will remind you. So dependency, what's a synonym for the word dependency? Correlation, yeah. So there's your first clue, right? Because what this number actually is the intraclass correlation. But the questions leading up to it are designed to trigger your memory as well. I asked for a significance test as to whether or not we had a significant random intercept variance, right? So you can tell me with a likelihood ratio test, that gets spit out by default in SAS as well. The test statistic for whether there is significant person dependency. So significant person correlation, that's the intraclass correlation. The amount of random intercept variance is what's tested against 0, but to express that as an effect size that ranges from 0 to 1, we can then convert that random intercept variance, which is actually a covariance across occasions, to a correlation. So the average correlation across months is the intraclass correlation. That is the effect size for the amount of person dependency due to mean differences over time. It is only one kind of person dependency, though. In this model, given that we only have a random intercept thus far, what that's saying is that there is only one kind of person dependency. There's only one reason that occasions from the same person are correlated. That's mean differences, which is captured by the random intercept, and that's it. That may not be the case, though, and that's the purpose of continuing on to test whether or not we have other random effects. Let's see, degrees of freedom equals 1 because you added 1 random intercept variance. The intraclass correlation reflects the proportion of between person variation. Then we went through the process of adding polynomial fixed effects and random effects of time. So the -2 log likelihood for a model predicting parallel linear change. Parallel is your key there. Parallel means I'm adding a fixed effect of linear time only, because the lines become non-parallel once we get a random effect in there. Then we have a -2 log likelihood for the next model predicting non-parallel linear change. That is accomplished by allowing each person to have their own random linear slope deviation, which is captured by this amount of variability in change per month. Then we end up with a common rate of change in the linear rate of change. That's a mouthful and a half. What is that thing, said more simply? That's my fixed quadratic rate of time, a common rate of change in the linear rate of change. The quadratic is how the linear slope changes per unit time. Common is another word for fixed, right? Everybody gets the same. Then we do individual differences in acceleration or deceleration. So that's random quadratic we're asking about there, and at this point everybody should have ended up with that as their best model. So then the results section walks through the process of augmenting the model with fixed and random effects of each type. In this instance, what we have is, let's see here. We have a positive rate of change coupled with a negative quadratic. So then what we have here is the linear rate of change decreased towards 0 non-significantly, so the fixed effect was non-significant in this case, by twice the quadratic effective month. So twice the quadratic is how the linear slope changes per unit time. There was significant individual variability. One thing I will point out, this is a popular source of confusion. When we added the random linear slope, that's a degrees of freedom equals 2, because it's the random linear slope variance plus its covariance with the intercept. When we added the random quadratic slope, that's a degrees of freedom of 3, because it's random quadratic slope variance plus the covariance with the random effects that are already there, intercept and linear slope. And then we're just asking you to find all the stuff from the model in this part here and compute random effects confidence intervals. Predicted well-being at month 1, that you didn't have to look for, that's your fixed intercept. Predicted well-being at month 6, that you have to ask for, that's an estimate statement. Total variance at any occasion should be found in the V matrix on the diagonal. And this one was a popular one to miss here. The fixed quadratic slope is indeed half the expected decrease towards 0 in the linear slope per month. So the quadratic itself is half the rate of acceleration. That means we need to multiply it by 2 to get it to be the actual rate of acceleration or deceleration. All right. How's that? Is that better, Amy? You're welcome. When I was a grad student here, Jim Jola, who I think is long since retired, said a phrase that I will take with me and I'll repeat it to you. It is better to be wrong than vague. So embrace your wrongness. Just don't be vague. Yeah, don't be vague, Aaron. Wave that hand. Section 4, right here.
So when you're talking about question 71, on that one, it's decreased because your quadratic slope is negative, right?
Yep.
But if ours is positive,
It would be an increase. An increase in the linear slope per month, which would be away from 0. Okay. If at any point you think you should have the right answer and I don't think you have the right answer, please tell me, because it's possible that I miscoded something. I am not a computer programmer. I did the best I could, and so I try to capture every possible instance of things, but if your data wandered into a territory I didn't anticipate, then it's possible that you may actually have a right answer. So if there's a question, please do let me know and I will look into it. Because yes, each of you has simulated data with the same story, but your parameters vary. Heather.
question 70, why is the
Yes, this. So in the model that has the fixed quadratic, anytime you have, let me back up. Anytime you have a main effect in the presence of an interaction, the main effect is the conditional main effect when the interacting predictor is 0. In this instance, if you have time and time squared, the effect of time becomes the linear slope specifically when the interacting variable, which is time, is 0. So if I were to draw, like this type of curve looks like this, I can't just talk about the linear rate of change at any occasion. I have to know where time 0 is, because if time 0 is over here, this is my linear rate of change. If I put time 0 over here and put time backwards instead, it'd be this one. So once you add a fixed quadratic, the fixed linear slope is specifically to where time 0 is. The same is true on the random side. If you have a random quadratic slope, the random linear time slope variance is specific to time 0 also. There. Does that help? Kinda? Let me see if I can say this any better. What did you think it should be instead of month 1? Across months. That's what it would be if we had just fit a linear model, because then the slope would be the same no matter where you've centered time. You can think of, like if you fit the same data with a linear model and then a quadratic model, the linear slope that you get before the quadratic goes in would be like the average linear slope, and then it becomes conditional to wherever 0 is once the quadratic goes in. Yes, okay. In this, this one had to do with the significance of the fixed quadratic effect. And in this case, it was non-significant. The confidence interval, it would be the fixed effect confidence interval would express that, yes, but not these random effects ones. This one describes the tendency for individuals to have rates of acceleration or deceleration. So this confidence interval for the quadratic overlaps 0, which means some people accelerate and some people decelerate. That question, though, refers to the estimate for the fixed quadratic right here, which was not significantly different than 0 in this instance. Do I need to say that again?
No, that makes sense.
Okay.
I'm not sure where that's significance.
For the fixed quadratic, it goes in the same table where you have estimate, standard error, degrees of freedom, t, and then p's at the end of the table. So if it's a fixed effect, you can stare at the output. If you're testing anything random, that's where a likelihood ratio test is needed. All right. Other questions? Alrighty then. Homework 6 is up. It's due in a week from Friday. It's long, so it might be a good idea to get started sooner rather than later. It's a piecewise model based on, actually, this story is based on a data analysis that I heard about at a conference. Pat Schrout actually had this dyadic data study of couples where one of the people was studying for the bar exam. And he tracked changes in the person taking the test stress and their partner's stress and all that kind of stuff. And I thought, that's a good example. I'm going to make up a story. So that's what the story is for this one. It's a piecewise model. You get to use maximum likelihood so that everything is some kind of likelihood ratio test. So I'm trying to make it easier on you since I want you to focus on the pieces. One thing, just to make sure that it's clear what I'm asking for in section 2, I'm asking for the values of the piecewise coding just to make sure that you set up your piecewise slopes correctly. So for instance here, question 9, enter the coded value of the phase 1 slope if occasion is 1. So when you write your statements to create the piecewise slopes, I'm asking you, what did you say the value for equation 1 should be for the first slope. That's just to make sure that you've got your model set up correctly. So don't go further unless you get these questions right, because otherwise there's an error in your piecewise coding, and that will throw everything else off. So have fun. And you have everything you need to be able to do that, since we finished piecewise models last week. Okay. Any other questions? No? All right. So I tend to hide at home if I don't have meetings or I don't have classes, because I'm a little more productive there. I also like working in my pajamas, just as a general rule. And whenever I drive into campus, I crank the radio and try and just let the universe find a good song for me to get pumped to come into class. I warm up my voice by singing along as loudly as I possibly can so that I'm ready to do this. And I got to share with you today's song that I heard on the way in. Let me see if I get the speakers going here. Video will play after ad. Is it going to work? Let me see. Oh, it's not going to work. You hear something. Okay, let me crank it. Creepy screen and back. Hello again. Now recording at home. All right, so let's see how we did here. There. Creepy screen and back. Hello again. Now recording at home. All right, so let's see how we did here. There. Number 1, model predicted outcome when time equals 4. So here's the model we're looking at: fixed intercept of 10, instantaneous linear slope when time equals 0 of 3, and a quadratic of -0.5, fixed quadratic. So to figure out what the model says the outcome should be at time equals 4, you plug in 4 everywhere where it says time. So this is no different than what you learned how to do in any other linear models class to create predicted outcomes. So it would work out to be 14. Okay, with me so far? All right, cool. Yes, now, how to ask SAS to do that for you. I asked you to figure it out yourself so that you could then hopefully translate this logic into a programming statement. So every time you see a word here in an estimate statement, it's referring to the fixed effect that goes with that word. So it's plugging in the coefficients 10, 3, and -0.5 respectively for each of these words. So to create a predicted outcome, it just needs to know how to combine the fixed effects. So in my equation here, I had 10, so that's my intercept 1. I need 1, 10 to start with. I need 4 linear slopes, and I need 16 quadratic slopes. When you put that all together, it would spit out this 14 along with the standard error and its p-value for whether or not it's different than 0. Okay. Any questions on that? All right. Now the trickier ones. What is the model predicted linear rate of change when time equals 4? So we forget the fixed intercept because that has nothing to do with what the linear effect of time will be at any occasion, and we focus only on this part. So the linear effect of time at time 0 itself would be 3. From there, we have to figure out what it would be at time 4 instead. So it is the quadratic fixed effect times the value of time at the desired occasion. And then we throw in a 2 because twice the quadratic is how the linear slope changes per unit time. That works out to be -1. That same idea implemented as an estimate statement means I need 1 of the linear fixed slopes, so I need 1 value of 3, and then I need 8 of the quadratic slopes because I have a time equals 4 times 2. And it knows that time by time is a negative value in this model, so it holds the negative value already. Okay, questions on that one? All right. Last one. Sort of a trick question, but not really. What is the model predicted quadratic rate of change at time equals 4? If you look at this equation, how many times does time by time show up? How many instances of time by time do you see in this model? Just one, right? That means it is unconditional. It doesn't interact with anything, so minus 0.5 is the effective quadratic time all the time. So what is the model predicted quadratic rate of change, period? It's better. So I'm starting on page 24. So here's an empty means random intercept model. You've seen this time and time again. These are the same 6-session response time data we've been playing with for several weeks now. This is what that empty means random intercept model would look like in NL mixed. So let me blow up the code here and walk through it. The first part here, these are options related to estimation that people who are smarter than me told me to pick. I'll just lay it out there. Why these are better than other similar things, I couldn't necessarily tell you, but I'm working off of examples that I've seen from other people like Don Hedeker and Walt Stroop and other people who are smarter than me who are trained in statistics, and I trust their judgment. One other piece to add here, this changes the convergence criteria to make sure that it's stricter, to make sure that the models are really done. It's not as, the default is looser than this one. So parms, we have to define every parameter that is to be estimated. What I'm estimating here is an empty means random intercept model. That has 3 parameters, right? Fixed intercept, random intercept variance, residual variance. So I have defined those with my very own names. I put F in front of things that are fixed, and then this is int for intercept. And I put var in front of things that are variances. So the variance of U0 and the variance of E, these are my names. After the equals sign are what are called starting values. These are values that the estimation routine starts on in trying to find the most likely values. Now you may ask yourself, how did I know what numbers to put there? Well, in this case, because this model is estimable in proc mixed, I use the right answers as starting values. If I were doing this for real, then we would start with a simpler model without any random effects to get good guesses for what the fixed effects would be, and then we would re-estimate it, updating the start values as often as necessary. If you don't have any idea what a start value should be, put 0 in. It may make it run longer, but it won't necessarily hurt anything. Then we're writing out the model itself. So this looks like the multi-level equations that we've seen thus far, where level 2 is first here. So I have B0I equals fixed intercept plus random intercept. And then I have pred y, which is the predicted value at level 1, equals my random intercept. So this is the same idea as what's in this equation here, just in words. The only thing that's missing for my level 1 equation that shows up here, this E, it goes in a different place. What we're saying is that response time is my outcome, has a normal distribution with a predicted value given by the model, right here, all that stuff, and it has a residual variance to be estimated because it's listed up here. I have a random line, just like in proc mix, in which I list any terms that I have defined to be random effects, such as U0I. I have told it that those U's have a normal distribution with a mean of 0. That's always the case for random effects, and a variance of a parameter that is being estimated right here. And then I define the nesting structure. I have an example of an estimate statement here Because estimate statements can do more stuff in NL mixed than they can in mixed, note that I'm asking it to compute an interclass correlation for me as a ratio of the estimated variance components. Proc mixed does not allow you to refer to variances in estimate statements, but NL mixed does. So this is a very handy feature if you're doing anything in which you need to get linear combinations of variances. For instance, I've been working on some analyses with Mabel Rice about heritability. Child language people, ears up here. In which heritability is defined as twice the difference in interclass correlation between MZ and DZ twins. That's what heritability is. I can get that with an estimate statement. In NL mixed, I can't get it in proc mixed because proc mixed doesn't do estimate statements involving variance components. Questions on the code thus far? So just to review, I'm listing out my model parameters. I gave them starting values. I'm defining my level 2 model and my level 1 model. And then I'm telling it how my outcome is related to those equations. It is normally distributed with the predicted value given by the model. So that's fixed and random effects. And a residual variance also given by the model as a separately estimated thing. So if I did this same empty means random intercept model in mixed, it would look like this, where here's my random intercept variance, here's my residual variance, here's my fixed intercept. The output from NL mixed organizes everything in one table instead, so it still gives you -2 log likelihood. But then it just spits out the estimated parameters in the order in which you listed them on the parm statement. So here's my f int, which based on my name, I know that's the fixed intercept. Here's my random intercept variance, and here's my residual variance. NL mixed does not have REML. It only has ML. So that is one potential limitation. On the output, you get a few extra columns that you don't normally get in proc mixed, although you can ask for them. This is the fixed effect confidence interval for the intercept. This is the confidence interval for the random intercept variance, and this is the confidence interval for the residual variance. So those are around the point estimates. This last column is a gradient. That is reminiscent from chapter 5. So if I have my happy little log likelihood mountain drawing on the board here, and I have my little slope that's traveling up the mountain, if I'm really at the top, the slope should be what? 0. That gradient column is the partial first derivative of the parameter with respect to the log likelihood. Partial first derivative of that parameter such that if the parameter is being well estimated, that gradient value should be 0. So I've included it in everything just so that you can scan this column for troubleshooting. If you see anything that is approaching non-zero, that's an indication as to where your model could be going wrong. So this is e to the 6, e to the 10, e to the 9. That means 0 to like the 9th decimal place, so it's pretty much 0. Here's another one that you already know, random quadratic time. This is what it looks like in mixed. So on the model line, I list out my fixed effects, including the fixed intercept, which is included by default. On the random line, I list out my random effects. Type equals BC means I have a single error variance that's equal across time with no covariance at level 1. In NL mix then, I'm listing out my fixed effects first, fixed intercept, fixed linear slope, fixed quadratic slope. I'm giving them start values that came from proc mixed. I'm listing out now all of my variances and covariances. So here's my random intercept variance, var u0. Here is the covariance between the random intercept and linear slope. Here's the linear slope variance. Here is the quadratic slope variance. Here's the covariance between the intercept and the, covariance between the intercept and, oh damn it, nope, here we go. Sorry, back up. Covariance between the random quadratic and intercept, covariance between the random quadratic and random linear, variance of the quadratic, and then e-variance. So I'm listing these out in the order in which they would appear in my G matrix. 1, 1, 2, 1, 2, 2, 2, 0, 2, 1, 2, 2.
So the order matters?
The order doesn't matter except to me in making sense of it. It matters in terms of specifying the random statement down here. You have to get them in the right order. So I'm listing out all of the parameters that are going to be estimated in this model, of which there are 10. Then I'm writing the model. I have 3 level 2 equations, fixed effect plus the random effect for each. So here's the, do I have the random quadratic model on here? I didn't paste it in here, darn it. Random quadratic, you've seen that one before at any rate. 3 level 2 equations. And then here's my level 1 equation, where I fill in the betas. Beta 0i being the intercept, beta 1i is the linear slope, beta 2i is the quadratic slope. E is left off because it shows up down here. And then I have 3 random effects. Therefore, I have to describe 3 means and a 3x3 G matrix. And this is in the order in which it shows up here. So 1, 1, 2, 1, 2, 2, 2, 0, 2, 1, 2, 2. Taking it just from the order that it shows up in the table. Here, 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 here. Okay. Let that sink in. Any that you want to hear again or ask about? All right. If not, then here's my mixed output, which you are well acquainted with at this point. And here's the same thing in NL mixed. I've separated out the fixed effects from all of the variance components. And ta-da. So in the code that follows, I'm switching from estimating variances to standard deviations. When the numbers get really big like this, they can be hard to find. So another trick I've gained from other people like Don Hedeker is to estimate standard deviations instead of variances to make the estimation a little more stable. Now here's our first model, negative exponential. So let me show you in pictures what this thing looks like. Slide 37 in lecture 6 here. We started this at the end of last time. So this is a nonlinear model that includes an asymptote. It can be either an upper asymptote or a lower one, and other variations of the model may have both. An asymptote in this context is basically the rate of performance if you were to practice infinitely. What is the best possible response time you can have? Where is the curve ending up at? So you can see the top left picture has curves with 3 different asymptotes. They all have the same shape. They all change the same amount, but they end up at a different place. The other parameter in the model is called an amount, and in this case, the asymptote is the same. The speed with which they get there is the same, but the total amount of change that has to take place until people hit asymptote differs. So the red person started out higher, had to change more to get down to their asymptote. And then last but not least, rate. So this is the nonlinear parameter. This is the one that's hard to estimate because it shows up within the exponential function. Here people started out the same, they end up the same, but the rate at which they hit asymptote is different. The blue person is faster. They come down faster to hit this point. So what's good about this model? If I were to say what these models predict at like time 10, what would happen? It stays the same, right? They don't come back up. This isn't some bullshit quadratic where it like doesn't make any sense because it comes back down or it goes back up when it shouldn't. It actually stays where it's supposed to. So this is a theoretically nicer model in that sense, that it makes predictions that are realistic. And these different parameters correspond to different ideas about how people change. You can talk about, individual differences in optimal performance. You can talk about individual differences in the total amount of learning, which is a function of basically how far you started. And you can talk about the speed with which people learn. These are ideas that readily map onto different theories. So here's what it's going to look like. The level 2 part is going to look the same in structure to all of the models that we've seen so far. Each beta has a fixed part and a random part. Fixed is the part that everybody gets. Random is the part that you get as your own deviation for which we estimate a variance. The catch is in the definition of each beta because it's different than usual. Up to this point, beta 0I has always been what? Intercepts, yeah. It's a level parameter. It describes some point basically on the y-axis. In this case, it's a level parameter but of a different kind. It's an asymptote. Beta 0I is the asymptote for each person. The best response time they would ever have given infinite practice. Beta 1I is the amount. So previously it's been a linear slope or the first slope. Now this is an amount parameter. It governs the total amount of change that has to take place from where you start to where you end up. And inside the exponent here is beta 2, which is the rate parameter, which is multiplied by time. So this is what I mean when I say nonlinear in the parameters, this chunk right here. In our previous models, it's been beta 1 times time plus beta 2 times time squared, or beta 1 times slope 1 plus beta 2 times slope 2. This is beta 1 times e to the beta 2 times time. It's a nonlinear function. That's why proc_mixed can't do it. So in this case, since proc_mixed can't do it, I'm going to come up with start values by starting with a model that just has the fixed effects, just so I can get decent start values for those, and then we'll layer in the random effects one at a time. Can you guess how we'll figure out if each fixed effect is significant? Yep, stare at the output, wald test. Can you guess how we'll figure out if each random effect is significant? Model comparison, log likelihood test. Yeah, same as usual. Same rules, same procedures, different piece of SAS to be able to specify this model. So let's see it. Here's my first one. So I'm showing you this as an example not only of an exponential model, which I find useful in a lot of situations, but also just how to use NL mixed in general. If there's ever a model that you come across in a book that there isn't readily available software for, or you think of a model that you want to estimate, something that is available with a tweak, and you can't figure out how to estimate it, you can do this. I don't know what it's called in Stata, but I'm quite certain there is something like that. Scott, do you know? No? I'm quite certain there is. I'm quite certain there's not in SPSS. I'm quite certain there is an R as well. I just don't know what it is. And M+ is its own beast that people have figured out how to trick it to do all kinds of things. So here's my fixed effects model. I have my fixed asymptote, my fixed amount, and my fixed rate. Now, I did not pull these numbers out of my ass. In fact, I pulled them out of someplace more meaningful. I pulled them out of the shape of the curve. So let me go back up to the curve that we're fitting here. This is my saturated means model prediction. If I had to make a guess as to where this line would end up if we made these people practice for the rest of their life, it's still kind of going down at this point. If I just hazard a guess, I'm going to say like maybe 1600 milliseconds, somewhere in there. And if I had to say how much total change did they have in response time, I'd say, you know, 300, maybe 400 milliseconds total between the top and where they're going to end up. And the fact that they're going down means that my rate parameter is going to be negative. So just taking those pieces of information, I hazard to guess as to what my start values would be. The standard deviation of the residual variance, I think I pulled from either the total variance or just the residual variance. That one doesn't matter as much because that one's pretty easy to find relative to the random effects. So I'm starting out with a model that's E only, but has the 3 fixed effects that define the negative exponential curve. Therefore, my level 2 equations just have the fixed effects. My pred y, this is my asymptote plus my amount times e to the rate times time. That came straight out of the books that I found. And then here, given that I'm estimating the standard deviation of e instead of the variance, I put in the squared term. Here's my trail of breadcrumbs, reminding myself what the hell these things mean later. The interpretation of the fixed effects, as well as the actual residual variance that's predicted by the model instead of in the standard deviation metric. And then alternatively, you can express this model with an intercept rather than an amount, so I added those back together to get that. Here are some examples of estimate statements then predicting what the model says the mean would be at each occasion, where you just fill in the level 1 equation and substitute in a value for time. So about a second later, it spits out my answers. Here's what it came up with from my asymptote, 1675. That's actually not too far off from what I guessed. The total amount of change is 284 on average, and the rate parameter is a negative 0.7. So on average, they end up at 1675. When they started out, they were 284 milliseconds higher than that, and they came down at this rate. Each of those fixed effects then potentially has a random effect to go with it. And here's the other estimates that I asked for. So in picking up a random intercept, I pick up one variance. I add my random intercept here. That means I pick up a random line in which my single random effect has a mean of 0 and a variance of that thing. I have 8404 as my -2 log likelihood relative to 9,000 and something. Yeah, that's significant. We get to keep my random asymptote. So then at this point, the model would look like this top one, parallel bendy curves. Everybody gets a different asymptote, but right now the amount and the rates are the same. So we pick up a random amount, allowing people to have individual differences in how far they have to come down to get to their asymptote. Add that to the beta 1 line, pick up another random effect, extend the G matrix accordingly. Is the random amount variance significant? -2 log likelihood difference says yes. Here's my random effects confidence intervals for that model. And then I tried to add a random rate and I got this. Quadrature accuracy could not be achieved. It means it can't do it. So I tried every other trick in the book to try and get a random rate to estimate, and it wouldn't work. So then we end up with a model that looks like this. So here's my random asymptote, random amount fixed rate model. It does a pretty good job on the mean side. It does not do a very good job on the variance side. So this line here, it's markedly off relative to the others. As with the other models, we looked at absolute fit, which we can do via likelihood ratio tests since we're in ML. And the means model fits absolutely. We can add in session-specific contrasts. The variance model does not. So it does a good job on the mean side. It doesn't do a good job on the variance side. There's only 2 random effects instead of 3, which may be part of the problem. Wake up! So how many of you are looking at this and going, yeah, I'm never going to effing do that. That's just not going to happen. That's not in my future. Anyone? I'll tell you, because as somebody who writes models a lot, having to write all of this out every single time is a major buzzkill. Major. So let me show you how to trick ProcMix into doing something that looks a lot like this. Log time. Slide 41. Here's an example of if you take your time variable, your linear slope that we started out with like 2 weeks ago, natural log transform it. In SAS, it's log. In Excel, it's ln. The black line in each of these pictures is what you get if you put in a linear slope for that log transformed variable. The top pictures are plotting the predicted value against the original time variable. The bottom pictures are plotting it against log transform time. So a linear effect of log time works out to be something that looks a lot like an exponential curve. If you add in a quadratic effect, then you hit something that looks even more like an exponential curve. Like, look at that blue line. Doesn't that look nice? Yeah. It takes your linear effect and it either dampens it or picks it up, depending on the direction of the quadratic. So this is something I did not put in the book, but that I've used increasingly often since then, and it's totally going in if I ever get a chance to redo it. Log time is a way to trick yourself into an exponential model using software that you know how to do. So let me show you that one. Log time equals log of session. So I'm on page 32. Now one catch. Why did I use the original version of session and not any other version? Any math whizzes in the house? What's a log of 0? Not defined, not a thing. So you have to start with a time variable that doesn't have zeros in it. So by logging session, the log of 1 is 0. So then I end up with the same type of session 1 as my reference point that I do in any of the other models that we've got. So the only catch here is figuring out what the value is for log time to be able to predict the outcome at particular occasions. So I put this in the Excel spreadsheet that goes with this example. The log of 1 is 0. The log of 2 is that. The log of 3 is that, and so on. So here's my log time. To be honest, I have a hard time interpreting this number, because it's like for every log time increase, response time goes down by 156 milliseconds. So this is the point at which I cry uncle and I make a picture. And look at that. Yeah. Isn't that nice? Log time. It accounts for just about as much variance as all the other models did. We can have random log time. Same idea. We're back in REML. We can do a log likelihood comparison. See if it's significant. Yes, it is. Let's test absolute fit in the same way that we did before with session contrasts. We get absolute fit on the mean side. So that yellow line is not significantly different than the black line. Basically, those fit equal. It approximates the means. On the variance side, no good. The yellow line for the variances does not match the original black line. So let's throw in quadratic log time. It's significant as a fixed effect, even though we already had absolute fit. So now it's the green line, which does an even better job. We have a random log time to try and approximate the variance side. -2 log likelihood comparison, and voila, it's significant. Test of absolute fit, non-significant. We win. So, putting it all together. Here's a comparison of everything that we did in the last 2 weeks. We did random quadratic original time, did not fit on the mean side, did not fit on the variance side, but adding any other polynomial effects really wasn't warranted. We had a piecewise model that does fit but makes really no sense because I picked the knot at an arbitrary point. Negative exponential that fit on the mean side but not the variance side, likely because we couldn't get the random rate to converge. And now I have this new random quadratic log time, which fits better than anything else up to this point. And there's the prediction for random linear log time versus random quadratic log time. So the green line here, if you take a look, it looks really exponentially. Look at that. Yeah. So yes, NL mixed, great. Log time, close enough. There's your take-home message. So whenever you have the effect of a continuous predictor that logically either should shut off or dampen like this, log it. Log it, log it, log it. How's that? So I know I rushed through a lot of that because I'm not going to hold you accountable for it, but I wanted you to see it. And of course I had the video for posterity. So now we're ready to change gears completely for next time. So any questions before we adjourn? No questions. Well then I'll let Survivor play us out and office hours start now.